So in this video, we're going to start to think about how we could also calculate delta H reaction. So 7.3 and 7.4 have shown two ways that you can calculate delta H reaction. This is another way. So when we start to think about this, we can start to look at different reactions. So we can use delta H, not F. So Hess's law requires equations. So we can start to think about what equations might be available to us. So a heat of formation is the formation of any compound. So delta H, not F, is the standard enthalpy of formation to form 1 mole of any substance. So this degree sign is pronounced not, N-A-U-G-H-T. And this means at standard state, which is 1 atmosphere, 25 degrees Celsius, and 1 mole. And delta HF, or HF, is the enthalpy to form 1 mole from the elements. So an example would be 1 mole of carbon solid, in this case graphite, plus 2 moles of hydrogen gas together forms methane. And the heat of formation in this case is negative 74.6 kilojoules. Whoa, that's not a line. Kilojoules per 1 mole of CH4. So in this case, we can calculate delta H reaction for lots of things from a formation reaction. So there are tables of values for the formation of all compounds, or you can use other values in order to come up with this. So we can identify heats of formation from a table, but it's important to note that the formation of an element in its standard state is 0 kilojoules. Basically, we need to think about it. If you can get the element in that state naturally, there is no effort required to form that. If it requires you to heat it, or in order to make it, then it has a heat of formation value. We know that delta H reaction is equal to the H of the products minus the H of reactants. So we can use these standard values in order to calculate delta H. Where does this sign here means the sum. It's the sum of the delta H not F values for all of the products minus the sum of the delta H not F values for the reactants. So this equation is going to allow us for any equation, provided we have access to either a table in the question or an appendice. There's published tables online. We can find this information in lots of places. But we can then calculate those for different values. So it is the sum of all products minus the sum of all reactants. So if we have this equation, using the standard enthalpy table shown on the right, determine delta H reaction for the following reaction. So we know that delta H reaction is equal to the sum of the delta H not F values for the products minus the delta H not F, the sum of the reactants. So these are all in kilojoules per mole, and so we need to multiply by the number of moles that we see in the calculation. So in this case, it's going to equal 4 times delta H not F of NO plus 6 times delta H not F of H2O. And that's going to be minus 4 delta H not F of NH3 plus 5 delta H not F of O2. So now, with access to the table, we can start to plug in values. So we have 4 times 91.3 plus 6 times, oh, which one of these values do we need? So this is liquid, so this one is the right value. Notice that the second H2O has the wrong state. So it would be negative 241.8, and that's going to be minus 4 times the value for ammonia, which is negative 45.9 plus 5. And we don't see O2 in this table, but we know that O2 gas is its native state, so that's going to be times 0. So this is just going to become 0. So we can start to plug these values in, and we get negative 1085.6 minus a negative 183.6. And so the delta H reaction is going to be equal to negative 902 kilojoules. So let me move that back over. So for these type of calculations, you'd be provided a table or access to a table, and then we can calculate delta H reaction for the following things based on the delta H values provided. So let's look at another example. So the thermite reaction, which is Fe2O3, is highly exothermic. So what is the delta H reaction using the standard heats of formation table? So we still know that delta H reaction is equal to the sum of the delta H not F for the products minus the sum of the delta H not F for the reactants. So again, we can plug this in. So it's going to be delta H not F of Al2O3 plus 2 delta H not F of Fe minus 2 delta H not F Al plus delta H not F of Fe2O3. So in this case, both of the standard states are going to drop to 0. So we are going to have the heat of formation for aluminum, which is negative 1,675.6 minus negative 824.2. And subtracting a negative is just like adding. So delta H reaction is equal to negative 851.4 kilojoules. So make sure that you find the right state or other information. So let's look at a third example that's slightly different. So given the following equation of copper oxide plus H2 gives us copper solid plus H2O, we know that the delta H reaction here is negative 129.7 kilojoules. So I'd like to solve for delta H naught F of copper oxide. And then it's going to ask, what is the enthalpy change if 3.203 grams of copper is created? So these two questions are independent. They're just both about the same reaction. So for A, we know that delta H reaction is equal to sum of the delta H not F for the products minus, the sum of delta H not F for the reactants. So from here, we just need to plug in values. So if we know it is negative 129.7 kilojoules equals the sum of the delta H not F of copper plus the delta H not F of H2O minus the delta H not F of CuO plus delta H not F of H2. So we know that both the heat of formation of copper and hydrogen gas are 0. And so we can plug in a value for the heat of formation of liquid water. So it's negative 129.7 kilojoules equals negative 241.8 kilojoules minus delta H, not F, of copper oxide. So we need to solve for delta H, not F, of copper oxide. And so when we move let's move this over a little bit so we have a little bit more space. So it's going to equal negative delta H, not F, of copper oxide. So when we move the negative 241 to the other side, it will be 241.8 minus 129.7, and that's going to give me 156.1. Now, it's important to note that this is a negative delta H, not F. Therefore, delta H, not F, of copper oxide is equal to negative 156.1 kilojoules. So in this case, we can see the difference between these, and we can see that it's just a chemical or an algebraic equation in order to get this answer. So that's how you would solve part A. Part B is the opposite, is a different type of calculation. So what is the enthalpy change if 3.203 grams of copper is created? We know that the heat of reaction is in kilojoules per mole, but in this case, it's per mole of everything in the equation. So we just need to know how many moles of copper we have. So for B, we're going to first determine how many moles of copper we have. So we have 3.203 grams of copper. We're going to divide that by the molar mass, which is 63.55 grams in 1 mole of copper. And then I'm going to go ahead and multiply that by the delta H reaction, which is negative 129.7 kilojoules, and that's in 1 mole of copper. Now, if the balanced equation had something else, we would need to account for that. So in this case, it's going to be negative 6.537 kilojoules. So we can use the heat of formation to calculate delta H reaction. If we have delta H reaction, you could back calculate any of the heats of formation. As a reminder, the heats of formations come directly out of a table, either provided in the problem, accessible in the homework system, accessible online via Google, or frankly, anywhere else that you could Google the heat of formation or identify that textbook or an online repository.